Welcome to Sleeping Researcher, your peaceful gateway to the wonders of science, narrated softly to help you drift into restful sleep. Here, we explore the universe's most fascinating mysteries with gentle words and a tranquil pace, designed to calm your mind as you learn. Now, before I start, I just want to spend this short time and give thanks to all my dear listeners. It has been 3 weeks since the start of this narration reading journey. The growth has been astonishing, and I truly appreciate that people are listening and enjoying my narrations. Once again, thank you. Tonight, we embark on a slow journey to the vast cosmic dance of galaxies, those immense collections of stars, gas, and dark matter that float through space. What happens when galaxies collide? At first thought, such a tremendous event might sound chaotic or violent, yet the reality is far more graceful and mesmerizing than one might imagine. In this narration, we will uncover how these colossal structures meet and merge, shaping the universe over billions of years. We will explore the subtle forces at play and the surprising consequences that ripple across space and time. Before we begin, if you enjoy this calm exploration of the cosmos, please like this video and subscribe to Sleeping Researcher. Your support helps us continue to bring soothing scientific stories to lull you into peaceful rest. Now, settle into a comfortable position as we slowly unravel the mysteries of galactic collisions and the beautiful transformations they inspire in our ever-changing universe. Imagine a vast cosmic stage where immense islands of stars, gas, and dark matter drift slowly through the fabric of space. These islands, known as galaxies, are not solitary or unchanging entities. Instead, they engage in a slow and graceful dance, guided by gravity and time. Over millions or even billions of years, galaxies can approach one another, drawn together in a complex interaction that can lead to a spectacular event, a galactic collision. This cosmic ballet is a fundamental process shaping the universe, revealing that galaxies are dynamic systems subject to constant evolution and transformation. Such encounters challenge our perception of the universe as static and unchanging, inviting us to explore how these colossal structures influence one another and what consequences arise from their interactions. When galaxies collide, the process unfolds over vast stretches of time, far beyond a human lifetime. Unlike collisions we might imagine on Earth, these events are more intricate and gentle. Stars within the galaxies are typically too far apart to crash directly into each other. Instead, the gravitational forces exerted by the two colliding galaxies distort their shapes, triggering waves of star formation as clouds of gas compress and ignite new stars. These interactions can dramatically alter the appearance of each galaxy, stretching spiral arms into elongated tails, or merging two well-defined galaxies into a single, larger system. The delicate balance of forces at play during these encounters highlights the vast scale and slow rhythm of cosmic evolution, reminding us of the timeless nature of the universe. Beyond their visual spectacle, galactic collisions have profound consequences for the structure and future of the galaxies involved. The merging process can funnel gas toward the galactic centers, often feeding supermassive black holes and triggering energetic phenomena such as active galactic nuclei or quasars. This influx of material can change the rate of star formation, sometimes leading to bursts of rapid stellar birth, or conversely, to the exhaustion of gas and a decline in new star creation. Moreover, as the galaxies settle after their cosmic encounter, their stellar populations mix and redistribute, creating new configurations and morphologies. These transformations provide a glimpse into the life cycle of galaxies and the forces that govern their continual metamorphosis. Understanding these outcomes helps astronomers piece together the history of our own Milky Way and the broader universe. The study of galactic collisions also offers insight into the nature of dark matter, an elusive substance that does not emit light but exerts gravitational influence. During collisions, dark matter halos surrounding galaxies interact in ways that can be inferred from the motion of visible matter and gravitational lensing effects. Observations of colliding galaxies thus serve as natural laboratories for exploring the distribution and behavior of dark matter on large scales. This interplay between observation and theory deepens our understanding of fundamental cosmic components and their roles in shaping the universe. As we continue to observe galactic interactions across the cosmos, we uncover new layers of complexity in these grand celestial events. Galaxies are vast, gravitationally bound systems composed of countless stars, clouds of gas and dust, and an enigmatic component known as dark matter. These immense assemblies can range from dwarf galaxies with just a few billion stars to giant elliptical galaxies containing trillions. The stars within a galaxy are often grouped into various structures, such as spiral arms, dense cores, or diffuse halos, all woven together by the invisible threads of gravity. Beyond the luminous matter we can see, dark matter forms a halo around each galaxy, providing the gravitational glue that holds these cosmic islands together. This complex composition means that galaxies are not merely collections of stars, but dynamic ecosystems where matter interacts across vast scales, evolving over billions of years. Understanding galaxies in this holistic way helps us appreciate their remarkable scale and complexity. Galaxies are the fundamental building blocks of the universe, organizing matter on grand scales and serving as the cradles of star formation and cosmic evolution. When galaxies collide, it is not a simple merging of two static objects, but a profound gravitational dance that unfolds over millions to billions of years. As these colossal structures approach each other, their mutual gravity begins to distort their shapes, pulling stars, gas, and dust into elaborate tidal tails and bridges. Despite the immense energies involved, the vast spaces between stars mean that individual stellar collisions are extremely rare. Instead, the interstellar gas clouds within the galaxies often collide. compressing the gas and triggering intense bursts of star formation, known as starbursts. These events can illuminate the galaxies with brilliant new stars, dramatically altering their appearance. The gravitational interaction also stirs the dark matter halos, redistributing the unseen mass and influencing the future dynamics of the merged system. These interactions are not merely destructive, but are catalysts of transformation, reshaping the galaxy's structure and composition over time. Galactic collisions can lead to the formation of entirely new types of galaxies. For example, when two spiral galaxies merge, their orderly rotating disks may be disrupted, eventually coalescing into a more spheroidal, elliptical galaxy with older stellar populations and reduced star formation. This process contributes to the diversity of galaxy shapes observed in the universe today. The merger also feeds gas toward the central regions, potentially fueling the growth of supermassive black holes that reside at the core of most galaxies. These black holes can then emit powerful jets and radiation, influencing their surroundings in complex ways. The interplay between star formation, black hole activity, and the rearrangement of stars and gas during collisions illustrates the deeply interconnected nature of galactic evolution. Each collision is a unique cosmic event, leaving indelible marks on the structure and fate of the galaxies involved. Observing galactic collisions across the universe provides a window into the dynamic processes that have shaped the cosmos since its earliest epochs. These events are more common in the distant past, when galaxies were closer together, reflecting the ongoing growth and assembly of large-scale cosmic structures. By studying the remnants of past collisions and the systems currently interacting, astronomers can reconstruct the history of galaxy formation and better understand the forces driving cosmic evolution. Moreover, analyzing these collisions sheds light on the nature of dark matter and the role it plays in galactic dynamics. The intricate patterns and consequences of galactic encounters reveal the universe as a place of continual change and profound interconnectedness. As we deepen our exploration of these magnificent cosmic interactions, we come closer to unraveling the mysteries of the universe's grand design. Galaxies, vast assemblies of stars, gas, dust, and dark matter, are not stationary islands in the cosmic ocean. Instead, they drift slowly through space, their paths governed by the invisible pull of gravity. Over billions of years, this gravitational dance brings galaxies into contact, drawing them closer until their boundaries blur and intertwine. These encounters are far from sudden collisions like crashing cars. Rather, they unfold over millions or even billions of years, a slow and majestic merging of cosmic giants. As galaxies approach each other, their shapes begin to distort under mutual gravitational forces, creating elongated arms and tidal tails that stretch across space. This gradual process highlights the universe as a place of constant flux, where even the largest structures are in motion, responding to the subtle tug of gravity that governs all matter. Each interaction, unique in its scale and outcome, contributes to the evolving tapestry of the cosmos, reminding us that change is the only constant in this vast expanse. When galaxies finally collide, their stars rarely smash directly into one another due to the vast distances separating them. Instead, the gravitational forces at play trigger waves of star formation as clouds of gas are compressed and stirred by the encounter. These bursts of new stars can light up the merging galaxies with brilliant clusters, temporarily transforming them into luminous beacons across the universe. Meanwhile, the interstellar gas and dust within the colliding galaxies interact more directly, creating shockwaves and fueling the birth of young, hot stars. In some cases, these energetic interactions may even awaken dormant supermassive black holes at the galaxy's centers, causing them to emit intense radiation as active galactic nuclei. Through this complex interplay, galactic collisions act as cosmic catalysts, shaping the structure and chemistry of the resulting merged galaxy. The aftermath is a transformed system, often more massive and structurally distinct, reflecting the profound consequences of these slow cosmic dances. Beyond the immediate spectacle of star formation and structural distortion, galactic collisions have long-term implications for cosmic evolution. The merging process redistributes dark matter halos enveloping each galaxy, blending their gravitational influence and altering the motion of stars and gas within the new system. Over time, this can lead to the formation of elliptical galaxies, which are generally more common in densely populated clusters where collisions are frequent. These elliptical galaxies often lack the prominent spiral arms seen in younger systems, presenting a more spheroidal shape and a calmer, more stable environment. The collision also stirs the galactic core, sometimes triggering new dynamical processes that influence the growth of central black holes. Studying such mergers helps astronomers piece together the life cycles of galaxies, revealing how they grow and evolve through a series of interactions that span billions of years. In this way, galactic collisions are not just isolated events, but fundamental episodes in the ongoing story of the universe's expansion and transformation. The motions and collisions of galaxies are also key to understanding the elusive dark matter that permeates the cosmos. By observing how galaxies distort and move during encounters, scientists can infer the presence and distribution of this invisible substance. Dark matter does not emit light or energy, yet its gravitational influence shapes the paths and fates of galaxies in profound ways. Colliding galaxies provide natural laboratories where researchers can test models of dark matter behavior, comparing predictions with actual observations. These investigations deepen our comprehension of the universe's fundamental components and highlight the interconnectedness of visible and invisible matter. Through the lens of galactic motion, we see that the cosmos is governed by forces both seen and unseen, moving in a delicate balance that orchestrates the grand cosmic symphony. As our gaze extends further into space and time, these insights guide us toward new horizons in understanding the universe's deepest mysteries. When galaxies collide, the event is not a sudden crash as one might imagine with smaller objects, but rather a slow and majestic dance that unfolds over millions of years. These immense structures, each containing billions of stars, vast clouds of gas and dust, and unseen dark matter, approach one another under the influence of gravity. As they draw closer, their shapes begin to distort, tidal forces stretching and pulling at the edges of each galaxy. Stars within these galaxies rarely collide directly due to the enormous distances between them, yet their gravitational interactions alter stellar orbits, sometimes flinging stars into new regions of space. The process can take hundreds of millions to billions of years, a reminder of the vast scales and patient rhythms that govern the cosmos. On this grand stage, galaxies merge, exchange material, and transform in ways that are both subtle and spectacular, revealing a cosmic choreography far beyond everyday experience. One of the most striking consequences of galactic collisions is the triggering of intense bursts of star formation. As the gas and dust clouds within each galaxy interact, they can compress under gravitational forces, collapsing to form new generations of stars. These starbursts light up the merging galaxies, often making them appear brighter and more vibrant in the night sky. At the same time, the turbulence caused by the encounter can funnel gas toward the central regions, potentially feeding supermassive black holes and igniting active galactic nuclei. This inflow of matter and energy can profoundly alter the evolutionary path of both galaxies involved. The merging process thus acts as a catalyst for change, reshaping the structure, chemistry, and energetic output of the galaxies over time. In this way, collisions serve as both an end and a beginning, dissolving old forms and sparking new ones in the ever-evolving cosmic landscape. Beyond the immediate effects on stars and gas, galactic collisions influence the large-scale structure and future dynamics of the galaxies themselves. Merging galaxies often settle into new, more massive elliptical galaxies, a process that can erase the distinct spiral arms characteristic of many disk galaxies. During the merger, the combined gravitational forces redistribute angular momentum and energy, causing the final galaxy to assume a more spheroidal shape. This transformation affects the distribution of stars and dark matter alike, creating complex, layered structures that astronomers study to understand galactic evolution. Additionally, the remnants of these collisions may contain streams and shells of stars, relics of the gravitational interactions that sculpted them. These features offer clues about the history and timing of past collisions, helping scientists piece together the life stories of galaxies across the universe. The slow unfolding of these changes reminds us that cosmic time operates on a scale humbling to the human mind, where even the mightiest structures are transient and ever-changing. While the vastness of space means that individual stars rarely meet during galactic collisions, the gravitational encounters can cause fascinating phenomena such as the formation of tidal tails, long streams of stars and gas pulled out into intergalactic space. These structures stretch for tens or even hundreds of thousands of light years, glowing faintly as they drift away from the main bodies of the merging galaxies. Tidal tails are evidence of the immense gravitational forces at play, and their shapes and sizes help astronomers reconstruct the dynamics of the collision. Occasionally, these tails can become sites of new star cluster formation, continuing the cycle of cosmic creation. Moreover, the interplay between the visible matter and the dark matter halos enveloping each galaxy further shapes these features, underscoring the intricate connection between the seen and unseen components of the universe. Observing and modeling these interactions continues to refine our understanding of how galaxies grow, evolve, and sometimes cannibalize one another in the vast cosmic web. Galactic collisions unfold in a variety of forms, each defined by the relative sizes, masses, and trajectories of the interacting galaxies. One of the most common types is known as a minor merger, where a large galaxy gently absorbs a much smaller companion. In these encounters, the larger galaxy's gravitational influence dominates, often pulling the smaller galaxy apart and integrating its stars and gas into its own structure over time. While the overall shape of the larger galaxy may not drastically change, these minor mergers can stimulate bursts of star formation as clouds of gas compress under tidal forces. This process enriches the larger galaxy with fresh material and subtly alters its evolution. The smaller galaxy, meanwhile, may be stripped of its stars and gas, leaving behind a faint stream or shell of remnants that orbit the main galaxy. Such interactions, though less dramatic on a grand scale, contribute significantly to the steady growth and complexity observed in many galaxies across the universe. More dramatic are the major mergers, where two galaxies of comparable size and mass engage in a slow, intricate dance that often culminates in their complete unification. These colossal collisions can last hundreds of millions of years, during which gravitational forces violently disrupt the galaxy's original shapes. Spiral arms may twist and distort, cores may approach and eventually coalesce, and vast clouds of gas can compress and ignite intense waves of star formation. The chaotic gravitational interplay stirs up massive tidal tails and bridges of stars and gas, stretching far into the intergalactic medium. Over time, the merging galaxies lose their distinct identities, often settling into a new elliptical galaxy with a more spheroidal shape. Major mergers can also trigger the feeding of supermassive black holes at galactic centers, leading to energetic phenomena such as quasars. This transformative process illustrates one of the universe's most powerful mechanisms for reshaping galactic structure and fueling cosmic evolution. Not all galactic encounters result in full mergers. Sometimes galaxies pass each other in what is called a grazing encounter or a flyby. In these situations, the galaxies come close enough for their gravitational fields to interact significantly, but their relative velocities and trajectories prevent a complete merger. Instead, the close approach can induce tidal distortions, pulling stars and gas into elongated tails or warping the galactic disks. These interactions may trigger localized bursts of star formation, and in some cases they can perturb the orbits of stars and gas clouds, influencing the internal dynamics of each galaxy. After the encounter, the galaxies continue on their paths, altered but separate, perhaps to meet again in the distant future. Such grazing encounters demonstrate the diversity of galactic interactions and reveal how even brief gravitational dances can leave lasting impressions on the structure and activity of galaxies. Beyond these main categories, astronomers observe a spectrum of collision scenarios, each with unique consequences, shaped by factors such as the angle of approach, relative speed, and the amount of gas present. Some collisions involve multiple galaxies in groups or clusters, resulting in complex gravitational interactions that can trigger cascades of mergers and encounters. In dense environments, these repeated interactions can strip galaxies of their gas, quenching star formation and leading to the gradual transformation of spirals into more passive, elliptical galaxies. Additionally, the interplay between the visible components and the surrounding dark matter halos modulates the gravitational forces at work, influencing how energy and momentum are exchanged during collisions. As our observational capabilities improve, capturing these diverse interactions in greater detail, we deepen our appreciation for the intricate and dynamic processes that govern the life cycles of galaxies. When galaxies begin their slow cosmic dance toward collision, the dominant force orchestrating their encounter is gravity. This fundamental interaction, though invisible, exerts a powerful influence over vast distances, drawing galaxies inexorably closer together. As these enormous collections of stars, gas, and dark matter approach, gravitational tides stretch and tug at their structures, causing dramatic deformations. The once symmetrical spiral arms may become elongated, distorted into sweeping arcs that extend far beyond the original boundaries of the galaxies. These stretched features, known as tidal tails, are composed of stars and gas pulled outward by the competing gravitational fields. The process resembles the tidal forces the Moon exerts on Earth's oceans, but on a scale millions of times greater. Such distortions reveal the profound sensitivity of galactic forms to gravitational interactions, even when the galaxies do not directly collide head-on. In some cases, the gravitational influence between colliding galaxies creates bridges of matter, connecting their distorted disks with streams of stars and gas. These stellar bridges serve as tangible evidence of the exchange occurring between galaxies, where material is pulled from one to the other. These connections can trigger bursts of star formation as gas clouds compressed within the tidal structures collapse to form new stars. The gravitational interplay not only reshapes the galaxies, but also reconfigures their internal dynamics, redistributing angular momentum and energy. These changes can result in the migration of stars and gas to different regions, sometimes funneling material toward the galactic centers, where it may feed supermassive black holes or ignite intense starburst activity. The complexity of these gravitational effects underscores the intricate balance and sensitivity of galactic ecosystems during encounters. The streams of stars and gas torn from their host galaxies do not simply vanish into the void. Instead, they form extended structures that can span hundreds of thousands of light years, tracing the paths of previous encounters. These streams often persist long after the initial collision, slowly dispersing into the intergalactic medium or eventually reaccreting onto the remnant galaxy. The morphology of these streams provides astronomers with valuable clues about the history of galactic interactions. By studying their shapes and trajectories, scientists reconstruct the gravitational forces at play and the sequence of events during collisions. In addition, the fate of the gas within these streams plays a crucial role in the future evolution of the galaxies involved. Gas-rich streams may replenish depleted reservoirs, sustaining star formation, while gas-poor or stripped systems may become quiescent, their stellar populations aging without renewal. These outcomes further illustrate how gravity governs not only the shapes we observe, but also the broader life cycles of galaxies. It is also important to consider the invisible yet substantial role of dark matter in these cosmic encounters. Surrounding each galaxy is a vast halo of dark matter, whose gravitational presence far outweighs that of the visible stars and gas. During collisions, these dark matter halos interact and merge, modifying the gravitational landscape in which the visible components move. This interaction can enhance tidal effects or stabilize certain structures, influencing the ultimate shape and fate of the merging galaxies. The combined gravitational potential of both dark and luminous matter determines the efficiency of energy dissipation and angular momentum transfer, critical factors that dictate whether galaxies will fully merge into a single system or pass through each other in a more gentle encounter. Observational and simulation studies increasingly reveal that understanding these dark matter dynamics is essential to comprehending the full complexity of galactic collisions. Contrary to popular imagination, when galaxies collide, they do not do so with the sudden violence of crashing cars or exploding fireworks. Instead, these cosmic encounters unfold over hundreds of millions to billions of years, a slow and deliberate dance governed by gravity. Galaxies are vast systems composed of billions of stars, but the distances between individual stars within them are so immense that direct collisions between stars are exceedingly rare. The stars themselves are like tiny points separated by enormous voids, making the idea of catastrophic star-to-star impacts highly unlikely. Instead, the gravitational forces between the galaxies pull and stretch their stellar and gaseous components, causing large-scale distortions such as tidal tails and bridges, but the individual stars mostly pass by each other unscathed. This slow progression allows us to observe these events at different stages and appreciate the complex gravitational choreography that shapes the future of the merging galaxies. As two galaxies begin their close approach, the gravitational interaction can trigger waves of star formation by compressing clouds of gas within each system. This burst of stellar birth is often observed as a brightening of the galaxies in ultraviolet and infrared light, signaling intense activity hidden behind clouds of dust. Yet, even amid this cosmic fireworks of new stars, the underlying collision remains a gradual process. The galaxies may orbit each other several times, their shapes twisting and warping with each pass, before finally settling into a new, often larger structure. The star's orbits are rearranged, and gas may funnel towards the center, fueling the growth of supermassive black holes or igniting central starbursts. Still, this transformation occurs over many millions of years, a testament to the vast scales and gentle rhythms of the universe. Importantly, the gaseous and dark matter components of the galaxies behave differently from the stars during these encounters. While stars largely sail past one another, the interstellar gas clouds can collide and shock, dissipating energy and altering the dynamics of the merging system. These interactions can strip gas from the galaxies or concentrate it in the core, influencing future star formation and the morphology of the remnant galaxy. Meanwhile, the dark matter halos merge and reshape the gravitational environment, guiding the movement of stars and gas alike. This interplay of components creates a complex and evolving structure that can result in elliptical galaxies, irregular systems, or even the reformation of spiral patterns. The slow pace of these collisions invites us to contemplate the patient forces sculpting the cosmos, far from the instantaneous chaos often imagined. Observations of interacting galaxies across the universe, along with sophisticated computer simulations, have deepened our understanding of these slow-moving encounters. From the famous antennae galaxies to the ongoing merger at the center of the Virgo cluster, each example reveals unique details about the processes at play. These studies emphasize that rather than abrupt, destructive events, galaxy collisions are transformative episodes that recycle stars and gas, redistribute angular momentum, and seed new cosmic structures. The gentle yet profound effects of these mergers contribute to the grand evolutionary story of galaxies, shaping the universe across cosmic time. This perspective helps us appreciate the universe as a place of continuous, graceful change, rather than sudden cataclysm. Understanding the slow dance of galactic collisions also informs our view of our own Milky Way's future. In about 4 billion years, our galaxy is expected to begin a prolonged encounter with the Andromeda Galaxy. a journey that will unfold over billions of years and eventually merge the two into a giant elliptical galaxy. This impending event underscores the patient rhythms of cosmic change, where vast distances and timescales govern the interactions of immense structures. The stars within each galaxy will mostly avoid direct collisions, continuing to orbit in new patterns shaped by gravity's persistent pull. This slow and majestic process invites us to reflect on the enduring nature of cosmic evolution and the quiet grandeur of the universe's unfolding story. As galaxies gently intertwine in their cosmic ballet, an extraordinary transformation unfolds deep within their sprawling arms. The immense gravitational forces at play during these collisions begin to compress vast clouds of gas and dust, the raw materials for star formation. This compression is not a sudden burst, but rather a gradual intensification of pressure that causes these clouds to collapse under their own gravity. As the density rises within these regions, the conditions become ripe for the ignition of nuclear fusion, marking the birth of new stars. This phenomenon, known as a starburst, can dramatically increase the rate of star formation compared to the galaxy's usual, more measured pace. These starbursts illuminate the galaxies with a renewed brilliance, often outshining the combined light of all their existing stars. The newly formed stars tend to be massive and short-lived, burning fiercely before ending their lives in spectacular supernovae. The energy and shock waves released from these stellar deaths further stir the surrounding gas, sometimes triggering successive waves of star formation. However, this intense period of activity is transient, lasting tens to hundreds of millions of years. A brief yet luminous chapter in the life of a galaxy. During this time, the galaxy's structure may also be reshaped as tidal forces stretch and warp its spiral arms, giving birth to striking visual features like extended tidal tails and star clusters. The consequences of these starburst episodes reach far beyond the immediate creation of stars. The massive stars formed during these bursts emit powerful winds and radiation that can expel gas from the galaxy's core, regulating future star formation and influencing the galaxy's evolution. Additionally, the enrichment of the interstellar medium with heavier elements produced by supernovae plays a crucial role in shaping the chemical complexity of subsequent generations of stars and planetary systems. This cosmic recycling ensures that each wave of star formation builds upon the legacy of those that came before, weaving a continuous thread in the tapestry of galactic evolution. Observations of distant galaxies reveal that starbursts are not uncommon in the early universe, where frequent collisions and mergers were part of the cosmic landscape. These intense periods of stellar birth helped to shape the galaxies we see today, influencing their size, shape, and composition. In the quieter present-day universe, starbursts remain dramatic reminders of the dynamic forces at work, acting as natural laboratories that allow astronomers to study how stars and galaxies evolve in tandem. As we continue to unravel the mysteries of these stellar nurseries, we gain deeper insights into the intricate processes that govern the life cycles of galaxies, including our own. As the starbursts gradually subside and the newly formed stars settle into their orbits, the galaxies continue their slow journey toward eventual merger. The interplay of gravity and gas dynamics will persist, setting the stage for further transformations. In the quiet aftermath of these stellar fireworks, the galaxy's evolution continues, shaped by the enduring forces of attraction and motion. This ongoing process invites us to contemplate not only the birth of stars, but also the enduring rhythms of change that define the universe. As two galaxies draw closer in their cosmic dance, the gravitational forces at play begin to reshape not only their stars and gas, but also the very heart of each galaxy. The intricate gravitational tug-of-war disrupts the calm reservoirs of gas that have long rested in the outer regions, sending streams of this material surging inward. This inward flow of gas acts like a cosmic river, funneling vast amounts of matter toward the galactic centers, where supermassive black holes reside. These black holes, often millions to billions of times the mass of our Sun, lie in wait, seemingly dormant in the vast darkness. Yet, as the feeding begins, their presence becomes dramatically apparent. The influx of gas and dust into the central regions provides a rich source of fuel for these supermassive black holes. As the material spirals inward, it forms an accretion disk, a swirling maelstrom of hot gas heated to extreme temperatures by friction and gravitational forces. This process can release enormous amounts of energy, sometimes outshining the combined light of all the stars in the galaxy. When a supermassive black hole is actively accreting matter in this way, it is known as an active galactic nucleus, or AGN. In some cases, the energy output becomes so intense that the galaxy transforms into what astronomers call a quasar, a luminous beacon visible across billions of light years. The awakening of these supermassive black holes has profound consequences for their host galaxies. The energy unleashed can drive powerful outflows and jets of particles at nearly the speed of light, pushing away gas and dust from the galaxy's center. This feedback mechanism can regulate star formation by clearing out the very material needed to birth new stars, effectively halting the creation of stellar nurseries. In this way, the black hole's activity acts as a cosmic thermostat, influencing the growth and evolution of the galaxy itself. Such interactions highlight the intimate connection between the smallest and largest scales in the universe, where the fate of countless stars is entwined with the hunger of a single, gargantuan entity. Observations of merging galaxies at various stages reveal a spectrum of activity, from gentle feeding to violent outbursts. These cosmic encounters offer a unique laboratory for understanding how galaxies evolve over time and how the most massive black holes grow through the accretion of matter during such tumultuous events. The interplay between gravitational forces, gas dynamics, and black hole activity paints a complex picture, one where chaos and order coexist. It is in these moments of transformation that the universe reveals its capacity for both destruction and creation. A balance maintained through cosmic cycles spanning billions of years. As the colliding galaxies gradually settle into a new equilibrium, the once violent feeding of their central black holes begins to wane. The quasar fades, leaving behind a galaxy transformed by the passage of time and the influence of its awakened core. Yet, this is not the end of the story, but rather a new chapter in the ongoing evolution of galaxies. The remnants of these interactions continue to shape the structure and behavior of their hosts, setting the stage for future encounters and growth. In this quiet aftermath, we are reminded of the delicate interplay between cosmic forces and the profound impact of supermassive black holes on the grand tapestry of the universe. When two galaxies collide, the graceful spiral arms that once defined their elegant shapes begin to distort and blur. These majestic structures, composed of billions of stars, clouds of gas, and dark matter, are pulled and stretched by immense gravitational forces. As the galaxies entwine in their cosmic dance, tidal forces trigger waves of star formation, lighting up regions rich in gas and dust. Yet, over millions of years, the distinct spirals lose their coherence, their orderly rotation disrupted by the chaos of the encounter. Stars are scattered into elongated streams and shells, creating a complex and irregular pattern. Gradually, the galaxies merge into a single, more spherical form, often resembling an elliptical galaxy. This transformation illustrates a profound aspect of cosmic evolution, where collisions do not merely destroy, but also reshape and renew. Elliptical galaxies, unlike their spiral predecessors, lack the defined arms and abundant gas that fuel ongoing star formation. Instead, they are dominated by older, redder stars, giving them a smooth, featureless appearance. The collision process effectively exhausts much of the available gas, either by converting it into new stars during the initial burst, or by expelling it through powerful winds driven by supermassive black holes and stellar explosions. This depletion curtails future star formation, leaving behind a galaxy that slowly ages and dims over billions of years. Such morphological transformation is one of the key pathways through which the universe's diverse population of galaxies evolves. It reminds us that even in the vastness of space, change is constant, and the outcomes of these grand encounters can be both destructive and creative. Beyond the visible changes in shape and star formation, colliding galaxies also influence the distribution of dark matter halos enveloping them. As these invisible structures merge, they deepen the gravitational well of the resulting galaxy, affecting the motion of stars and gas within. This deeper potential well helps stabilize the newly formed elliptical galaxy, allowing it to maintain its structure over cosmic timescales. Additionally, the dynamical friction during the merger causes central supermassive black holes to spiral toward each other, eventually coalescing into a more massive black hole. This process releases enormous amounts of energy, sometimes observable as gravitational waves, rippling across the fabric of space-time. Thus, galaxy collisions are not only agents of morphological change, but also key players in the growth and evolution of some of the universe's most enigmatic objects. The transformation from spiral to elliptical galaxies through collisions also holds clues to the broader narrative of cosmic structure formation. In the early universe, frequent interactions among young, gas-rich galaxies contributed to the rapid buildup of massive elliptical galaxies observed today. These ancient collisions set the stage for the large-scale organization of galaxy clusters and superclusters, where elliptical galaxies often dominate the dense cores. By studying these processes, astronomers gain insight into the life cycles of galaxies and the environmental factors that shape their destinies. Each collision, each morphological shift adds a new chapter to the story of how the cosmos evolves from chaos to order, weaving complexity from the interplay of gravity, matter, and time. As we observe galaxies in various stages of collision and transformation, we are invited to contemplate the delicate balance of forces that govern their fates. The serene glow of an elliptical galaxy belies the tumultuous history of its formation, a silent testament to the power of cosmic encounters. These grand mergers, while violent in process, ultimately create stable, long-lived structures that enrich the universe's diversity. In this ongoing dance of creation and destruction, galaxies continue to evolve, setting the stage for future interactions and the ever-changing mosaic of the cosmos. To grasp the immense scale and complexity of galactic collisions, scientists turn to computer simulations that stretch the limits of modern technology. These digital models, developed by institutions like NASA and the European Space Agency, allow us to visualize the slow-motion ballet of galaxies interacting over billions of years. By inputting data about gravitational forces, dark matter distribution, and the physical properties of stars and gas, these simulations recreate the intricate processes that shape the cosmos. We witness spiral arms twisting and warping, star clusters dispersing, and colossal streams of gas drawn out into vast tidal tails. Each frame of these simulations is a frozen moment in an epic narrative, revealing how gravity sculpts the universe on grand scales. Within these virtual environments, galaxies draw near with quiet inevitability, their mutual attraction overcoming the vast distances between them. As they approach, gravitational tides stretch their shapes, triggering waves of star formation as gas clouds compress and collapse. Yet, despite the apparent chaos, the stars themselves rarely collide, separated by immense space, even within their crowded neighborhoods. Instead, the galaxy's dark matter halos entwine, merging into a single, larger gravitational well. Over millions of years, the original structures dissolve and reform, often resulting in a new, more massive, elliptical galaxy. This transformation illustrates how cosmic violence gives way to stability and how the universe recycles its components into ever-evolving forms. The consequences of these galactic encounters extend beyond mere shape changes. They influence the very life cycle of stars and the growth of supermassive black holes. Simulations reveal that the inflow of gas during collisions can feed central black holes, igniting periods of intense energy release known as active galactic nuclei. This energetic feedback can regulate star formation by heating or expelling gas, effectively shaping the future potential of the merged galaxy. Moreover, the mergers can displace star clusters, create shells and ripples in the stellar distribution, and redistribute angular momentum. These subtle signatures, when observed in real galaxies, provide clues to their tumultuous pasts, allowing astronomers to piece together cosmic histories written across billions of years. Beyond individual galactic transformations, simulations also offer insights into the broader evolution of the universe's large-scale structure. Colliding galaxies are not isolated events. They occur within clusters and filaments, where gravitational interactions sculpt the cosmic web. By modeling these environments, scientists can explore how repeated mergers contribute to the hierarchical growth of galactic systems, from small groups to massive clusters. This ongoing process reflects the dynamic nature of the cosmos, where matter continuously assembles and reassembles, guided by the invisible hand of gravity. Through these simulations, we gain a deeper appreciation for the interconnectedness of cosmic phenomena and the enduring patterns that arise from seemingly chaotic beginnings. As we peer into these simulated futures, we also glimpse the destiny of our own galaxy, the Milky Way, which is on course to meet the Andromeda Galaxy in several billion years. The models predict a slow, graceful merging process, culminating in a vast elliptical galaxy that will drift quietly through the cosmos. This anticipated encounter invites reflection on the transient nature of cosmic structures and the perpetual transformation that defines the universe. Through the lens of simulation, we are reminded that even the most majestic and seemingly eternal formations are part of a continuous cycle of change and renewal. As the Milky Way and Andromeda galaxies draw nearer, their mutual gravitational attraction begins to weave a complex cosmic dance. Over the span of several billion years, these two immense collections of stars, gas and dark matter will slowly spiral towards one another. This gradual approach is not a violent crash, but rather a delicate intermingling of vast stellar populations and swirling clouds of interstellar matter. As the galaxies interact, tidal forces will stretch and distort their shapes, pulling long streams of stars outward into spectacular tidal tails that arc through space. This process, while dramatic on a galactic scale, unfolds so slowly that any individual star, including our Sun, may only experience subtle changes in its local environment. The collision itself will be a majestic transformation, a slow blending of two magnificent spiral galaxies into a new, larger elliptical form. The luminous arms of the Milky Way and Andromeda will gradually dissolve, replaced by a more spheroidal shape that will shine with the combined light of countless stars. The consequences of this cosmic encounter are profound, but far from catastrophic for the stars themselves. Given the vast distances between stars, direct stellar collisions are extraordinarily rare. Instead, the gravitational interplay will rearrange orbits and trigger waves of star formation as clouds of gas compress and ignite new stellar nurseries. These bursts of creation will briefly illuminate the merging galaxies with fresh brilliance, a reminder that, even in the midst of transformation, the universe continually gives birth to new light. For any hypothetical observers on a planetary system within the merging galaxies, the night sky would change dramatically over millions of years, with the neighboring galaxy growing larger and brighter until it eventually fills the sky. Yet, despite this upheaval, the vast majority of planetary systems will remain intact, orbiting their stars as before, quietly witnessing the grand cosmic evolution unfolding around them. Our solar system's journey through this galactic merger is a narrative of resilience amid change. While the gravitational turbulence may nudge the Sun and its planets into new trajectories within the newly formed galaxy, the timescales involved are so immense that these shifts will be imperceptible within any human lifespan, or even the entire span of human history. Astronomers predict that, in about 4 billion years, as the Milky Way and Andromeda begin their final embrace, our solar system will find itself in a different neighborhood of stars, perhaps farther from the center of the new galaxy or closer to its outskirts. This shift reminds us that while the cosmos is ever-changing, it also maintains a continuity that allows stars and their planets to endure through epochs of transformation. In this light, the merging of our home galaxy with Andromeda is not an ending, but a new chapter in the ongoing story of cosmic evolution. Beyond the immediate stellar and planetary effects, the merger of the Milky Way and Andromeda will reshape the dark matter halos enveloping both galaxies, influencing the gravitational landscape for billions of years to come. The union will create an immense combined dark matter halo, a hidden but vital framework that sculpts the motion of stars and gas within the galaxy. This invisible structure supports the stability and future growth of the new elliptical galaxy, guiding the paths of stars and the distribution of interstellar gas that may eventually fuel further star formation or feed the central supermassive black hole. In fact, the cores of both galaxies, each hosting a giant black hole, are expected to slowly spiral inward and merge as well, releasing a subtle but powerful ripple through space-time known as gravitational waves. These waves will ripple outward, a faint cosmic echo of the grand galactic embrace. This interplay of visible and invisible forces highlights the profound complexity and beauty inherent in galactic collisions. When galaxies collide, the vast distances separating individual stars mean that direct collisions between stars are extraordinarily rare. Solar systems, like our own, largely escape immediate destruction. Instead, what they experience are subtle shifts in the gravitational environment as the entire galactic structure reorganizes itself. As the stars from two galaxies intermix and the distribution of mass changes, the orbits of stars within their respective galaxies may be gently perturbed. Over millions to billions of years, these gravitational nudges can alter the paths of stars, potentially sending some on elongated orbits or causing them to migrate closer to the galactic center. Still, the vast emptiness between stars ensures that planetary systems remain largely intact, protected from the chaos of direct encounters. Despite the protective vastness between stars, the gravitational reshuffling that accompanies a galactic collision can influence the environments in which solar systems reside. Stars that once orbited calmly in the outskirts of their home galaxy might find themselves drawn toward denser regions as the merger progresses. This movement can expose solar systems to higher densities of interstellar gas and dust, possibly increasing the chances of encounters with molecular clouds or supernova remnants. Such changes in the local cosmic neighborhood might affect the radiation environment or the influx of interstellar material, subtly influencing planetary atmospheres or cometary activity within those systems. However, these effects unfold over immense spans of time, allowing planetary systems to adapt or endure without catastrophic disruption. The gravitational interplay during galactic collisions also affects the large-scale dynamics of star clusters and stellar streams. Some star clusters may be torn apart or scattered as tidal forces stretch and distort the merging galaxies. Others might be compressed, triggering new bursts of star formation from clouds of gas compressed by the changing gravitational tides. Solar systems embedded within these clusters could find themselves in environments rich with young, energetic stars, and perhaps influenced by the radiation and stellar winds they emit. Yet again, the direct impacts on individual planetary systems remain minimal, with the primary consequences being changes in the broader stellar neighborhood and the potential for new generations of stars to emerge from the cosmic upheaval. Over the longer term, the newly formed galaxy resulting from the merger will settle into a transformed gravitational equilibrium. Solar systems will find themselves orbiting within a different galactic potential, one shaped by the combined mass and distribution of stars, gas, and dark matter from both progenitor galaxies. This new gravitational landscape can influence the stability of orbits over billions of years, subtly modifying the trajectories of stars and their accompanying planetary systems. While these changes are profound on cosmic scales, the individual solar systems remain resilient, their delicate balance maintained amidst the evolving galactic environment. Such enduring stability amidst transformation offers a testament to the vastness and complexity of the cosmos. In considering the consequences for stellar systems, it becomes clear that galactic collisions are less about destruction on a local scale and more about transformation on a grand cosmic scale. The merger of galaxies orchestrates a slow, majestic dance of gravity and matter, reshaping the environments in which stars and planets exist, without directly wreaking havoc on their internal structures. This understanding leads us, naturally, to reflect on the broader consequences for the interstellar medium and star formation, where the collision's energy and turbulence ignite new processes and possibilities. When galaxies collide, the immense gravitational forces at play do more than simply blend two vast collections of stars, gas, and dust into one. These interactions often give rise to striking new formations that are as beautiful as they are scientifically fascinating. Among the most remarkable of these are ring galaxies, which emerge when a smaller galaxy plunges through the core of a larger one, triggering a ripple effect that propagates outward like waves on a pond. This gravitational disturbance compresses gas and dust in the larger galaxy's disk, sparking intense bursts of star formation along the expanding ring. The result is a luminous, circular structure dotted with young, bright stars, providing a vivid testament to the transformative power of cosmic encounters. These rings can span tens of thousands of light years and serve as natural laboratories for observing the complex interplay between gravity, gas dynamics, and star birth. Alongside ring galaxies, another fascinating consequence of galactic collisions is the formation of shell galaxies. These structures appear as faint, concentric arcs or ripples of stars that envelop the main body of a galaxy, resembling the delicate layers of an onion or the iridescent patterns on a seashell. Shells are believed to result from smaller galaxies merging into larger ellipticals, where stars from the absorbed galaxy are tidally stripped and settle into elongated orbits. As these stars reach the outer edges of their trajectories, they slow down and accumulate, creating visible shells that can persist for hundreds of millions of years. These features not only enhance the visual complexity of galaxies, but also provide astronomers with clues about the history and frequency of past mergers, revealing the hidden narratives written in the stars. The creation of rings and shells through collisions exemplifies how galactic interactions are agents of cosmic art, sculpting new and intricate forms from the raw materials of the universe. These structures do not merely decorate galaxies. They influence their evolution by redistributing mass and angular momentum, altering star formation rates, and sometimes even reshaping the overall morphology of the resulting system. The interplay between gravity and the interstellar medium during these encounters initiates complex feedback mechanisms, where shockwaves and turbulence can compress gas clouds, triggering starbursts, or conversely, expel material and quench future star formation. Through these processes, the universe continuously recycles and renews itself, weaving a grand tapestry of cosmic life that spans billions of years. As we observe these spectacular cosmic features, we gain deeper insight into the dynamic and ever-changing nature of the universe. The rings and shells formed in galactic collisions stand as enduring monuments to the slow, graceful transformations that shape galaxies over eons. They remind us that even in seemingly violent encounters, there is a profound beauty and order emerging from the chaos, a dance of matter and energy, choreographed by the fundamental forces of nature. This perspective invites us to explore further how the aftermath of such collisions influences not only the visible structure of galaxies, but also the hidden processes within their cores, where supermassive black holes and dense star clusters reside. When galaxies collide, it is not only their visible stars and gas clouds that interact, but also their expansive, invisible dark matter halos. These halos are vast, diffuse envelopes of dark matter that surround galaxies, extending far beyond their luminous boundaries. Though dark matter does not emit or absorb light, its gravitational influence is profound, shaping the structure and evolution of galaxies. As two galaxies approach and merge, their dark matter halos begin to intertwine and coalesce in a slow, gravitational dance. This merging process is gentle on a cosmic timescale, unfolding over millions or even billions of years, allowing the halos to gradually combine into a larger, more massive structure. This union of dark matter halos plays a crucial role in the subsequent formation and growth of the newly formed galaxy, providing the gravitational scaffolding needed to attract and hold gas and stars within the emerging system. The merging halos create a deep gravitational well that influences the motion of stars and gas, guiding the reshaping of the galaxy's structure and dynamics. As the dark matter halos merge, their combined gravitational field significantly affects the surrounding environment, especially within galaxy clusters, where many such interactions occur. These clusters are the largest gravitationally bound structures in the universe, and their evolution depends heavily on the behavior of dark matter. When individual galaxy halos merge, they contribute to the growth of the cluster's overall dark matter halo, increasing its mass and gravitational pull. This process fosters the accretion of more galaxies, gas, and dark matter, gradually building up the cluster's complexity and size. Furthermore, the merging halos can induce subtle shifts in the orbits of galaxies within the cluster, sometimes triggering new collisions or interactions. This interconnected dance of halos and galaxies drives the large-scale structure of the cosmos, illustrating how the invisible dark matter framework orchestrates the visible tapestry of stars and galaxies. Within the galaxies themselves, the merging of dark matter halos influences the internal processes that govern star formation and the growth of central black holes. The deepening gravitational potential well created by the combined halos can compress gas clouds, encouraging the collapse of matter into new stars. This can lead to bursts of star formation, illuminating the galaxy with fresh light born from the cosmic encounter. At the same time, the rearrangement of dark matter alters the gravitational landscape around the galaxy's core, potentially affecting the feeding cycles of supermassive black holes residing there. These black holes may experience increased accretion of gas, igniting energetic phenomena that ripple across the galaxy. In this way, the unseen dark matter halos subtly but powerfully guide the life cycles within galaxies, linking the macroscopic collision to microscopic processes. The merging of dark matter halos also provides insight into the nature of dark matter itself, a mysterious substance that remains elusive despite its dominant presence in the universe. By studying how halos interact and combine during galaxy collisions, astronomers can infer properties about dark matter's behavior, such as its collisionless nature and how it responds to gravity independently of ordinary matter. Observations of colliding galaxy clusters, for example, reveal that dark matter passes through collisions relatively unaffected, unlike the hot gas, which can be slowed or displaced. These findings help refine theoretical models and simulations, deepening our understanding of the cosmic web that dark matter weaves. The ongoing exploration of halo mergers thus not only illuminates galaxy evolution, but also opens a window into the fundamental physics governing the universe's most abundant matter. As we continue to unravel the complex interplay between dark matter halos and galactic collisions, we begin to appreciate the profound influence these invisible structures have on the grand scale of cosmic architecture. Merging halos not only unify galaxies, but also set the stage for the formation of vast galaxy clusters, shaping the large-scale environment in which galaxies live and evolve. This perspective encourages us to look beyond the stars and nebulae, toward the dark foundations that support and direct the cosmic dance. With this understanding, we can now turn our attention to the aftermath of these collisions, exploring how the energetic cores of galaxies respond and transform in the wake of such monumental encounters. When galaxies collide, the vast scales involved make these events some of the most magnificent and transformative processes in the universe. Unlike collisions on Earth, where solid objects crash and shatter, galactic collisions are more like slow, graceful dances. Galaxies are mostly empty space, so stars rarely collide directly. Instead, their mutual gravitational attraction pulls them closer, causing their shapes and structures to distort and intermingle. This interaction often results in streams of stars, gas clouds, and dark matter being drawn out into long tidal tails that stretch across millions of light years. Over time, the gravitational forces cause the galaxies to merge, with smaller galaxies being gradually absorbed by larger ones. This natural process, sometimes referred to as galactic cannibalism, plays a crucial role in the cosmic hierarchy, allowing massive galaxies to grow by consuming their smaller neighbors. The scale and duration of these mergers can span hundreds of millions to billions of years, making them slow-motion spectacles that reshape the very fabric of galactic neighborhoods. In the grand narrative of galaxy formation, this absorption of smaller galaxies by larger ones is fundamental to the hierarchical model where structures build up progressively over cosmic time. When a larger galaxy captures a smaller companion, the smaller galaxy's stars, gas, and dark matter become incorporated into the larger system. These events often trigger bursts of star formation as gas clouds collide and compress, igniting new generations of stars in brilliant, luminous displays. The influx of new material can also feed the central supermassive black hole, sometimes activating it as an active galactic nucleus that emits intense radiation across the electromagnetic spectrum. As a result, the larger galaxy evolves not only in mass but also in complexity, with new stellar populations, altered shapes, and enriched chemical compositions. This continual process of growth through mergers helps explain why many of the massive elliptical galaxies we observe today appear to be the end products of numerous past collisions and absorptions. These interactions are far from chaotic destruction. Rather, they are vital chapters in the story of cosmic evolution. Beyond the immediate consequences for the merging galaxies themselves, these collisions influence their environments on even broader scales. The gravitational disturbances can displace vast reservoirs of gas, spreading it into the surrounding intergalactic medium. This redistribution enriches the space between galaxies with heavier elements forged in stars, seeding future star formation elsewhere. Additionally, the merging process can alter orbital paths and velocities, shaping the dynamics of galactic groups and clusters. The newly formed, larger galaxies often settle into more stable configurations, sometimes becoming central, dominant galaxies within clusters. This central role further solidifies their influence on the evolution of their cosmic neighborhoods. Moreover, the dark matter halos enveloping merging galaxies also combine, deepening gravitational wells and affecting how matter flows on large scales. Through these cumulative effects, galactic cannibalism contributes not only to individual galaxy growth, but also to the sculpting of the universe's large-scale structure. The ripple effects of these ancient cosmic encounters continue to resonate through space and time. Observing galactic mergers in different stages across the universe offers us a window into this ongoing saga of growth and transformation. Some collisions are caught early, with galaxies visibly intertwined yet distinct, while others have long since merged into single massive entities. By studying these systems, astronomers gain insights into the physical processes governing star formation, black hole activity, and the behavior of dark matter in extreme conditions. Simulations complement these observations, allowing scientists to recreate and predict the intricate gravitational interactions that shape the galaxy's fates. Together, these approaches deepen our understanding of how the cosmos evolves, not merely through isolated events, but through a continuous cycle of interactions and assimilation. As we peer further into the universe's past, we uncover evidence that galactic cannibalism has been a driving force since the earliest epochs. guiding the assembly of the majestic galaxies we see today. With this appreciation for the dynamic nature of galactic mergers and growth, we can now explore the intimate consequences for the energetic cores of galaxies. These central regions, often home to supermassive black holes and dense star clusters, respond dramatically to the influx of matter and gravitational disturbances triggered by collisions. Understanding these responses opens the door to comprehending how galaxies regulate their own evolution internally, completing the cosmic picture from large-scale structure to the smallest, most powerful engines within. One of the most striking and well-studied examples of galactic collision is found in the antennae galaxies, a pair of interacting spiral galaxies located approximately 45 million light-years away in the constellation Corvus. Named for the long antenna-like tidal tails that extend far beyond their main bodies, these galaxies provide a vivid snapshot of the complex gravitational dance that occurs during a merger. Observations across multiple wavelengths, from visible light to infrared and X-rays, reveal a chaotic environment where clouds of gas and dust are compressed, triggering intense bursts of star formation. This cosmic fireworks display is a direct consequence of the collision, as the gravitational forces funnel material into dense regions, igniting the birth of countless new stars. The antennae galaxies thus serve as a natural laboratory, illustrating how galactic interactions can dramatically reshape their structures and fuel stellar nurseries. As these two galaxies continue their slow, intricate merger, their original spiral shapes become increasingly distorted. The gravitational tug-of-war stretches out long tidal tails of stars and gas, which can span hundreds of thousands of light-years. These features are not only visually stunning, but also tell a deeper story about the transfer of angular momentum and the redistribution of matter. Within the overlapping regions where the galaxies meet, the gas density rises sharply, providing the perfect conditions for star clusters to form in rapid succession. Some of these clusters are extraordinarily massive and compact, resembling proto-globular clusters that may survive for billions of years. Meanwhile, the intense gravitational interactions also cause gas to flow inward toward the galaxy's central regions. This influx may feed the supermassive black holes residing there, potentially triggering active galactic nuclei and powerful outflows that influence the surrounding interstellar medium. The antennae galaxies reveal more than just spectacular star formation. They also highlight the long-term consequences of galactic mergers. Over time, the two galaxies will lose their distinct identities and settle into a more stable, elliptical shape. This transformation is accompanied by the gradual exhaustion of cold gas, as much of it is either converted into stars or expelled by energetic processes linked to black hole activity and supernova explosions. The result is a galaxy that is less gas-rich and less prone to new star formation. Moreover, the merger-driven disturbances can dynamically heat the stellar populations, increasing the random motions of stars and thickening the galactic disk. These changes impact the morphology, kinematics, and future evolution of the remnant galaxy. By studying the antennae and similar systems, astronomers gain insight into how such mergers contribute to the diversity of galaxy types observed in the universe. Beyond the immediate visual spectacle, the antennae galaxies also serve as a reminder of the timescales involved in cosmic interactions. The collision and merger process unfolds over hundreds of millions to billions of years, a slow and patient transformation that shapes the destiny of galaxies. Each close passage between the galaxies stirs the interstellar medium, prompting waves of star formation and altering the trajectories of stars. These subtle yet profound changes ripple through the system, influencing the chemical enrichment, stellar populations, and central black hole activity. As such, the antennae provide a unique window into the dynamic processes that govern galaxy evolution, bridging the gap between isolated galaxies and the massive elliptical systems that emerge from these grand cosmic encounters. In observing the antennae galaxies, astronomers also refine their theoretical models of galactic collisions, matching simulations with real data to better understand the physical mechanisms at play. These studies illuminate how mergers can trigger feedback processes, regulate star formation, and ultimately shape the large-scale structure of the universe. The antennae thus stand as an exquisite testament to the power of gravity and time, showing us how the universe continually reshapes itself through the elegant complexity of galactic encounters. With this vivid example in mind, we can now turn our attention to the energetic cores of merging galaxies, where supermassive black holes and dense star clusters respond in remarkable ways to these cosmic events. When galaxies collide, they do more than simply merge their stars, gas, and dust. They become agents of profound transformation on a cosmic scale. These grand encounters, which unfold over hundreds of millions of years, serve as essential chapters in the universe's evolving story. The gravitational forces at work during such collisions redistribute matter and energy, rearranging the very architecture of space. This process contributes to the hierarchical growth of cosmic structures, where small galaxies coalesce to form larger ones, and clusters of galaxies grow ever more massive. As these systems evolve, they weave the vast cosmic web, a delicate lattice of filaments and voids visible across the observable universe. Galactic collisions, therefore, are not isolated events, but pivotal mechanisms driving the universe's large-scale structure toward greater complexity and diversity. The consequences of galactic collisions extend deeply into the realm of star formation and chemical enrichment. During a merger, clouds of gas within the galaxies are compressed and agitated, often triggering intense bursts of star formation, known as starbursts. These newborn stars, born in clusters, flood their surroundings with radiation and stellar winds, influencing the interstellar medium in dynamic ways. Over time, the cycle of star birth and death disperses heavier elements forged within stars back into space, enriching the gas that will form future generations of stars and planets. This gradual chemical evolution shapes the very conditions necessary for the emergence of complex matter and, potentially, life. Collisions thus act as cosmic forges, sculpting the composition and character of galaxies as they mature. Beyond star formation, the gravitational turmoil of galactic collisions can awaken the dormant giants residing in their centers, supermassive black holes. As the merger funnels gas toward the core, these black holes may begin to actively accrete matter, igniting luminous phenomena known as active galactic nuclei. The energy released in this process can drive powerful outflows and jets, regulating the growth of the host galaxy by heating or expelling gas that would otherwise form stars. This feedback mechanism plays a crucial role in maintaining the balance between galactic growth and quiescence, influencing the overall evolutionary path of galaxies. The interplay between merging galaxies and their central black holes reflects a delicate dance, one which shapes both local environments and the broader cosmic landscape. On even larger scales, galactic collisions contribute to the dynamic evolution of galaxy clusters and superclusters. As individual galaxies merge and interact, they affect the distribution of dark matter halos enveloping them, altering gravitational potentials that govern the motion of countless other galaxies within the cluster. These interactions can induce waves of star formation or quenching across multiple systems, subtly influencing the thermal state of the intracluster medium. Over billions of years, such processes help to refine the cosmic web's intricate structure, enhancing the filamentary networks that trace the universe's expansion and acceleration. In this way, collisions are part of a grand cosmic dialogue, linking the fate of individual galaxies to the evolution of the universe itself. Understanding the role of galactic collisions in cosmic evolution opens a window into the universe's ongoing creative process. Each encounter adds new chapters to the story of matter, energy, and structure, revealing how complexity arises from the interplay of fundamental forces. As we prepare to explore the energetic cores of merging galaxies, where supermassive black holes and dense star clusters respond in fascinating and sometimes unexpected ways, we begin to appreciate the intricate connections that bind the cosmos, from the smallest scales to the grandest. This perspective invites us to contemplate not only the mechanics of these phenomena, but the profound narrative they compose across space and time. As we stand on the threshold of a new era in astronomy, the advent of powerful instruments like the James Webb Space Telescope offers an unprecedented opportunity to observe galactic collisions in exquisite detail. These collisions, once enigmatic and veiled by distance and time, are now becoming accessible to our gaze through advanced infrared imaging and spectroscopy. By peering into the dense clouds of dust and gas that often obscure these cosmic encounters, researchers can study the birthplaces of stars triggered by the immense gravitational forces at play. These observations not only deepen our understanding of how galaxies grow and evolve, but also illuminate the complex processes that govern star formation, black hole activity, and the redistribution of cosmic material during these grand mergers. The intricate dance of colliding galaxies also reveals clues about the behavior of dark matter, the elusive substance that constitutes much of the universe's mass, yet remains invisible to direct detection. Through careful mapping of how galaxies distort and pull on one another, scientists can infer the presence and distribution of dark matter halos enveloping each galaxy. This insight is crucial for testing theoretical models of cosmic structure formation and for understanding the mysterious forces shaping the large-scale architecture of the cosmos. As telescopes continue to refine their sensitivity and resolution, the subtle gravitational signatures embedded within these colossal interactions will become clearer, enabling researchers to unravel the hidden scaffolding upon which galaxies assemble and transform. Moreover, the aftermath of galactic collisions offers a rich laboratory for studying the evolution of supermassive black holes that reside at their cores. When galaxies merge, their central black holes are drawn toward one another, eventually coalescing into more massive singularities. The process releases tremendous energy, detectable across the electromagnetic spectrum, and influences the surrounding environment by regulating star formation and shaping the galactic landscape. Future observations with next-generation telescopes will capture these dynamic phenomena in real time, helping to clarify the mechanisms behind black hole growth and the feedback effects that govern the balance between explosive activity and cosmic calm. These insights promise to deepen our grasp of the life cycles of galaxies and the central engines that power them. Beyond individual collisions, the broad survey of interacting galaxies across cosmic history allows astronomers to construct a timeline of galactic evolution, revealing patterns and variations in how these majestic structures assemble. By combining deep field observations with sophisticated computer simulations, researchers can recreate the sequences of past mergers and predict future interactions. This fusion of data and theory not only enriches our comprehension of the universe's dynamic past, but also guides our expectations for its unfolding future. As new discoveries emerge, they continually reshape our understanding of cosmic evolution, inviting fresh questions and inspiring further exploration into the profound processes that sculpt the heavens. In this unfolding narrative of cosmic discovery, each new insight gained from telescopes like JWST and its successors serves as a beacon, illuminating the complex interplay of forces that govern galactic collisions. The journey toward deeper knowledge is ongoing, propelled by curiosity and the relentless pursuit of understanding. As we continue to unravel the mysteries hidden within these grand encounters, we remain connected to the cosmos through the shared threads of matter and energy, time and space. The path ahead is rich with promise, guiding us toward ever more refined perspectives on the nature of the universe and our place within its vast expanse. Galaxies collide. It is not merely a moment of chaos, but a profound transformation on a cosmic scale. These immense structures, composed of billions of stars, clouds of gas, and vast amounts of dark matter, engage in a slow, graceful dance that unfolds over millions to billions of years. During these encounters, gravitational forces reshape the galaxy's forms, triggering waves of star formation as clouds of gas compress and ignite new stellar nurseries. While the vast distances between individual stars mean that direct collisions are rare, the gravitational intermingling profoundly alters their orbits and ultimately the destiny of the galaxies involved. Over time, these cosmic mergers can result in the birth of larger, more complex galaxies, often elliptical in shape, signaling an evolution in the structure of the universe itself. The consequences of galactic collisions extend far beyond the immediate spectacle. They influence the distribution of matter and dark matter, stirring the cosmic web that binds the universe together. These encounters redistribute gas and dust, sometimes funneling material towards central supermassive black holes, activating them and causing bursts of energetic phenomena observable across vast distances. Such processes contribute to the growth and evolution of these enigmatic cores, which in turn shape the galaxies that host them. Furthermore, the merging of galaxies plays a critical role in the life cycle of stars, recycling cosmic material and enriching the interstellar medium with heavier elements forged in stellar furnaces. Thus, galactic collisions act as engines of cosmic renewal, sustaining the ongoing cycle of creation and transformation. As we contemplate these monumental events, we recognize that galactic collisions are not destructive endpoints, but essential chapters in the universe's grand narrative. They remind us that change is an intrinsic property of the cosmos, a continuous flow of motion and energy shaping the very fabric of space and time. Through these interactions, galaxies grow, evolve, and give rise to new generations of stars and planetary systems, potentially nurturing the conditions necessary for life. In this way, the collisions echo a deeper truth. The universe is a dynamic, ever-changing entity, where even the most violent encounters serve a higher purpose in the unfolding story of existence. Our understanding of these processes deepens not only our scientific knowledge, but also our sense of connection to the cosmos. Ultimately, the study of galactic collisions invites us to reflect on the vast timescales and immense forces at work beyond our immediate perception. It humbles us with the scale of cosmic evolution and inspires awe at the delicate interplay of gravity, matter, and energy that sculpts the universe. These collisions, gentle in their own slow rhythm, are moments of rebirth and transformation, highlighting the ever-changing nature of all things. By observing and understanding these grand events, humanity gains a richer perspective on the origins and fate of the cosmos, and on our place within this magnificent, unfolding tapestry. As the universe continues to evolve, so too does our appreciation of its beauty and complexity deepen. In closing, galactic collisions stand as fundamental cosmic events that shape the destiny of the universe. They weave together the threads of matter and energy into new forms, guiding the evolution of galaxies and the cosmic structures they inhabit. Through these majestic encounters, the universe reveals its capacity for change, growth, and renewal on scales that transcend human experience. As we gaze into the depths of space and time, we are reminded that the cosmos is alive with motion and transformation, an eternal dance that continues to unfold long after we have ceased to watch. This profound realization connects us to the universe in a timeless way, inviting us to embrace the wonder and mystery of the cosmic journey.